this kind of slide kind of summarizes that, right? Like, I mean, this educational component, how can we enable other researchers to do work on it? How can we utilize the equipment better that's out there? And maybe how can we even integrate citizen scientists into these kind of approaches? So in this robot that I showed you that we had used in this online lab, we now try to make a much simplified version of that really students could use in kind of a robotics club, right? As I said earlier, we know about Lego Mindstorm, First League Robotics, and so forth, which really entices students to engage with these kind of media. And I don't think we really haven't tackled the life sciences or the vet sciences in that kind of space. And so we built this robot here, right, where you can, for example, program some simple dilution experiments with food colors here. You can also run more complicated experiments inducing different bacterial strains to show color reactions. Here, this kind of image shows, right, like you can have 4 different plates in there. You have a few ones with reservoirs, and you can have a small plate and do all sorts of mixture. This is all color. Ideas now with children who love colors, program interesting things, learning to program, develop these robots further, right? And how could we really get these kind of robotics clubs actually more into the life sciences as well? Here's another experiment with the same robot. So 4 solutions with salt, normal salt, right, but different concentrations. And if you now layer these different solutions over each other in the right order, you get a density gradient that is stable. If you do it in the wrong order, everything mixes up. So it's kind of a fun experiment to really understand density and program basically robot in order to do it. So we've built this robot. We also had a teacher in our lab over the summer, and we now want to get this into schools and kind of explore further, like how teachers really kind of like to use that. So I think I'm getting close on time. Should we finish up, or should I? Okay, so let me just maybe give a very more general kind of outlook of the ideas. In order to make any sort of interactive biology work, what you really need is obviously biology. You need something to stimulate. You need something to measure or sense. And if you look at your biology labs these days, most of devices don't have all these features. Like most microscopes you can see, or maybe then there are PCR machines or other things where you can really actuate something. But kind of the combination of both is not often there. If we now want to enable interactivity, especially kind of for making things online and other things, to really interact with the digital world that we're used to, we really can think of these devices having a digital input, a digital output. We call this biotic processing units, where you can have a digital stimulus or input that then gets transferred into physical actuation. The biology does something, there's a physical sensing, and then there's a digital output. And this has many reminiscences of CPUs and other kind of electronic chips, right? And we can also think about metrics of how to measure the performance of any such system. And I don't think I have time to do that, but the basic idea here is to measure somehow, and we use mutual entropy for that, is like how many experiments, or how many meaningful experiments could you actually do on a particular machine? And just to make this simple, if you just have 2 LEDs and you have a reaction time of 10 seconds, you can get 1 bit of information out of that. If you, for example, have 2 LEDs, you can actually double that. If you have a field of view where you can do many experiments in parallel, you can get much more out of that. And so if you think of, again, about scaling and how to have many people use it, these kind of measures are useful. So let me just go to the. Let me just stop here with this end slide. Coming back to the beginning, right? We can make lots of comparisons to electronics. If you think of modern biotech now, you can argue there's a certain 50-year lag between them. There's kind of the early foundations that were set, right? The early foundations of quantum mechanics and kind of discovery, structure of DNA, and so forth. There was a certain amount of time where the transistor was invented and integrated circuits. We have now similar chips like that, right? And we can, of course, also look at interactivity or games, which have been invented 50, 60 years ago in computer science. And back then it was actually not very clear what a computer game or what that actually should be and what this is useful for, but it's very culturally prominent now, right? And so I think in similar ways, maybe in very different ways, we will interact with these microscopic things and they will become part of our daily life. And I think it should be because biotech really influences us with novel ways, medical treatment possibilities, and so forth. Right? Okay, so that's what I want to say. So now, look forward to your questions. Yeah.
And Ingmar, if you go back to where you're showing the video of the robotics pipette experiment, I know that you talked about cell phones earlier, but I wanted to hear more about the collaboration options for when you're using that robotics biolab and how students can monitor those experiments with cell phones. Can you talk a little bit about that?
Okay, sure. So, so Mindstorms has sensors, right? So one of the things we first thought is like using a color sensor and letting it, for example, run with a robot right over the wells and basically reading out, for example, the different intensities. And that doesn't work very well. I mean, it roughly works, but it's not as great. So integrating kind of a camera would be good because then you could do lots of things. And now it's a question, how can you control everything at the same time? One way we want to do this is there's a shield out there which you can actually put on a Raspberry Pi that works essentially like the Mindstorm block. You would need slightly different programming language for it, but it's much more open. But then you could also use the Raspberry Pi camera, for example, for monitoring and taking images and things. We haven't really thought about integrating a cell phone with that. I mean, that's an interesting idea. You could, for example, assume you put the cell phone on there as well, have the cell phone taking pictures regularly. One thing I found is it's really an integration problem, especially if you want to have students do it, right? I think there's already a learning curve just for the Mindstorm programming language. If you now kind of mix 2 or 3 different things together that don't talk to each other well, how does one facilitate that? So that's certainly a question, yeah.
I guess my question was about the ethical slide that you showed.
Okay.
So, I mean, when I was watching your presentation, I said, well, they're just little cells, you know.
Okay.
Who cares that you're being weird to them? But what do you see as the obstacles coming up when, if this goes to scale and how it could develop, right? You could imagine it moving from little single-celled organisms to cats and mice.
Okay. So for me, it was always like it's about microscopic. But it was, if you bring it to museums or any sort of other ways, I mean, children usually don't care verbally directly, but maybe 10 to 20% of adults ask this as a question, like, are there ethical questions, right? You can say that the children sometimes say like, oh, tickle me, or don't torture this guy, or something, so which you could also interpret as some sort of ethical reflection, right? So I sat down with a bioethicist at Stanford and kind of really tried to tease this apart, like what does it mean? And there are a bunch of arguments that people could have. For example, oh, are you hurting them, right? Or today you do it with cells, but tomorrow you do it with monkeys or so, right? And so the ethical guidelines that, or suggestion that we put forward is, first of all, I mean, don't do anything that you do harm in any sort of way, right, or cause pain. And these single-celled organisms, I mean, don't have a perception of pain. They are not sentient, right? The second thing is you want to engage with the public and saying what you're doing here is something that you want to have a good outcome, right? You do this for educational purposes, so people really understand something, not just for violently engage with these cells, right? Then you can think of how do you somehow treat these cells with respect. I mean, it's an interesting question, what does it mean to respect a single cell, right? But, I mean, you can, if you think about your dog, you can engage with your dog by throwing a stick and having like this two-way interaction. You can have 2 dogs fighting and hurting themselves, right? And similarly here, the systems that we made, right, the cells, the stimuli, kind of physiological stimuli, the cells are moving naturally. So we don't hurt any cell. At the same time, if you think about your pizza, if you put them in the oven, you kill tons of cells there, right, of similar complexity, and that's the way it is, right? And the final thing is to somehow respect the perception of the person who's interacting with that. I mean, if you make games, I mean, make good games, but also don't make people feel bad, oh, am I now hurting them or something, right? Like giving them a positive experience. So I think that's kind of the framework that we're working in, and we're really on the good side. And of course, if you were going to higher and higher organisms, which I right now don't intend, you would have to be much more stringent of why are you doing it and what's happening. Yeah.
This isn't so much a question as a comment that follows up on the other. It seems like if it's related to supplying food, and all of a sudden we don't really care what happens to the creatures. So I'm wondering if there could be lessons built around food safety or something like that. Sorry.
Yes, so there's certainly one interesting aspect, right? Like if you feed someone who's hungry, you have a different standard if you say, "Oh, I just play," right?
People who eat animals are killing animals and eating them. You can't get more invasive than that, but because it's achieving a higher function, we allow it.
Yeah, so that's true, and there is also this notion. If you say we do an experiment here so that children can learn, just calling all of this an experiment, it has, in the perception of many people, a higher standard than if you say, oh, we make a game here that children can play with. So I think in our society we kind of value play less than education to some extent, but I feel that lots of play is actually how children learn, right? And so I think there's something that we don't have fully figured out in our heads, how we really look at these things.
Another thing that again isn't necessarily a question, it might even be an advertisement, but it also could get to the heart of the ethical issue. We have a technology having to do with micro-robotics that allows us to simultaneously control very small robots over
Okay.
something like a tabletop using magnetics. I know it seems like it's very important that there be real biology here as opposed to just simulation. But I'm wondering if there's kind of a middle ground where it's something physically moving.
Yeah, sure. So
not necessarily biological.
Sure, you could do live, you could do animated, you could do robots, right? I think lots of, certain studies show that you have a different emotional response or something if you know it's real versus it's not. And I mean that all of this is real because that's my personal interest to kind of go along this way. So did you want to have a quick question still, or you have to run?
Well, I do have somewhere to go right now, but I wanted to ask about the citizen science. You
Mm-hmm.
started to talk about citizen science and what the opportunities are for those kinds of interactions. For instance, if you're working in a school district that might not have the financial capabilities to fund this kind of work with their students, but there might be such great learning opportunities for those students to, even if it doesn't involve building these apparatuses and these pipettes, but being able to interact with the product of it and learn from it. Are there opportunities for them to do things like, or I don't know, yeah, but are there opportunities for them to engage through citizen science work?
So I mean, that's kind of the hope to go there. I mean, we haven't really done this. Citizen science has many flavors, right? One thing I'm envisioning is that people could go to our online server, play with it, do experiments, and discover new things, right, and contribute them. The other is, sure, people replicate the technology locally because we enable them with the building plans and everything, and then going out into the wild and doing things and discover. Yeah.
Just from a practical point of view, how robust are these euglena or the other organisms that you use? What kind of infrastructure would you need to deliver them? Do you need to keep things refrigerated, and is it like fresh food, or is it?
No, so the robustness, I mean, this was like a huge deal for us, and actually took quite a long time to get there. So the very first thing they showed with the paramecia, right, they're fine for like 50 minutes in the chamber, then you have to put new ones in. hard to culture. Like after 5 days, you need to order fresh ones. It was all hard. But with the Euglena now, you can really have a closed vial on your desk, just sunlight, and they are fine for weeks. And the reason is, I mean, they use sunlight, but they can also eat bacteria. And it's not just, I mean, Euglena are big cells. There's all sorts of other things on a small scale. And so it's really a stable, self-contained ecosystem that we are using here, and where we put the light on it, right? And then there's a little bit of additional logistics that we automatically kind of flush the chamber, like putting fresh organism in from time to time by automatically opening, closing a valve. And we're building more and more around it as we kind of have this close monitoring, right? Like taking images, measuring how many are there. So, but we really get to a point where it is like plug and play, right? Like a computer you can trust, you can turn it on and it works, right? And we're really getting there. And that's important because otherwise all these interactivities don't work.
Related to that, do you imagine that these organisms or microaquariums will be at only your central facility, many central facilities, or do you want to get it to the point where each school will have one as well, so they can, see the real thing with their eyes, and then also see the kind of remote.
So certainly it's important that you have both, right? That you can see it tactile in front of you and use kind of the online. I mean, I would hope and envision that the whole thing gets replicated. I mean, we have now a system that we can use to run educational studies and kind of service a bunch of partner schools, right? If you then really think about scale up, there becomes a question, I mean, would we find some commercial partner who has the capacity and the interest of kind of supplying this for a stable service? So if you think about a school supply company who currently ships all these organisms, I mean, maybe they could house one of these servers themselves, and so teachers would kind of pay for the time, or school would pay for the time. It would be rather cheap, and they could log on and do things from there. Would also be very interesting if kind of in a DIY manner, people or schools kind of start replicating, making it themselves.
Thank you so much.
Good. Thank you.
I appreciate you doing that.
Thank you.